This was how I described Faraday's law of electromagnetic induction in the past few videos. The induced voltage in a coil is proportional to the rate of change of the flux linking the coil. Now I want to fill in one detail about this law. Suppose that I have a coil like this, and the flux comes from, say, a magnet near the coil. It comes from the magnetic field coming out from the magnet. Okay. If I move the magnet, the flux linking the coil would change, and that would induce a voltage in the coil. Now in that sense, I can actually think of this coil like a battery. You know, if I have a battery, I can connect this battery to a light bulb. I can connect this to a light bulb, and if I connect this to a light bulb, the light bulb will light up. So in the same way, if the magnetic flux changes fast enough, the induced voltage would be enough to actually light up a light bulb to produce electricity. So in that sense, this coil is very similar to a battery. Now recall what we have learned about the battery. The battery supplies an EMF, an electromotive force. And this is the, if you remember, the work done to bring a unit charge, like 1 coulomb, around the circuit once. So that's the EMF. But there's something about this EMF. The definition of EMF is almost the same as the definition of voltage, but there's a difference between EMF and the voltage across the cell. And the reason is because some of the work has to be used to overcome internal resistance in the cell. And we have a similar issue here. The coil would produce a voltage if the flux changes, but there is the issue that the coil itself would have resistance. For example, if it's copper wire would be a very good conductor, but there would still be some resistance. So I can imagine that thinking about this as, say, the coil which has flux, which can link to the flux, and I can also think that a part of that there is some amount of resistance in along the copper coil, which I can represent say by a little box here. Right, this little box, for example, could represent all the resistance along this wire. So if that is the case, then what happens if I actually connect this coil to a light bulb? If I connect this to a light bulb, the bulb, it might actually light up if the flux changes fast enough to give a big enough voltage. But the thing is, the voltage that is actually produced from the coil, would be actually lower than if there is no resistance, because some work must be done to move charges through the resistance of this coil. So we can actually think of the effect of this quantity that is induced by the changing flux. We can actually think of it as an EMF. in the sense that if I connect this to a circuit, then this quantity, this EMF that is induced by the changing flux would move electric charge around this circuit, but some of it will be used to do work against the resistance inside the copper wire. Okay, and as a result, the actual voltage appearing across the coil is actually smaller than the EMF that is induced by the changing flux. So because of this, it should be more correct, right? It would be more correct, instead of calling this the induced voltage in a coil, to call it the induced EMF in a coil. Okay, because if we say the induced voltage in a coil, we usually think of the voltage as the actual voltage appearing across the coil, and that actually would be the same as the EMF if the coil is not connected into a closed circuit, right? If no current flows. But if it's actually connected in a closed circuit, then the moment current starts flowing, work will be used up to bring charges through the resistance of the coil, and then the actual voltage appearing across the coil would normally be smaller than the actual EMF that is induced by the changing flux. So from now on, it would be more correct to call this the induced EMF. Right. The next thing I want to talk about is the units of Weber. Weber, 1 Weber, which is written as 1 WP. Now, if you remember what Weber means, I have previously described this as the flux that you get if there is a loop with an area of 1 meter squared, so a unit area in SI units, and a magnetic flux going through it, with a magnetic flux density of 1 Tesla. Okay, so if I have this situation, then the flux which is equal to, assuming a uniform magnetic field, magnetic flux density times the area, and assuming that B is perpendicular to the area, then this would be, the flux would be 1 Tesla times 1 meter, 1 times 1, which is 1 Tesla meter squared. Okay, and we call this 1 Weber. Right, so the 1 Tesla meter squared is defined. It's in that sense we can think that it is defined to be 1 Weber. Now, but what I would like to mention here is that there is actually another way that the Weber is defined, and that is a definition which is decided by the international committee which agreed on the SI units, and this is how it is officially defined. Official in the sense that it's agreed upon by an international committee of scientists. Right. Let me clear this part up. I still need the EMF here. Let's look at the other way in which a Weber can be defined. Suppose that I have a loop. Say I have a loop. Okay, and suppose that I have a magnetic field going through it. Uniform magnetic field, and the area is A. So the magnetic flux linkage in this case, this would be phi equals to B times A, as we have understood this. And suppose that the magnetic field is changing in strength, then the flux would be changing, and a voltage or an EMF would be induced in the coil. Now I want to suppose that I can measure this voltage. So suppose I measure it with a voltmeter. Okay. Now, suppose that the magnetic field strength is allowed to decrease uniformly. Suppose that it decreases uniformly. Now I can imagine plotting a graph. Okay, suppose I plot the graph of the flux density against time. So suppose that in the beginning there is a certain flux density. In the beginning, the magnetic field has a certain strength. Now, as time passes, this magnetic field, the strength of this field, the magnetic flux density, is made to decrease uniformly, so that the flux falls in a straight line in the graph. Right? If it falls in a straight line, it just means that you can imagine that maybe every second or every 0.1 second, the flux decreases by the same amount. Right? At equal intervals in time, the flux will decrease by the same amount. That's what we mean by uniformly. So the flux it decreases uniformly. And if we plot that as the graph, it would naturally be a straight line, because at every equal interval it comes down by the same amount. Okay. Now, if this decreases uniformly, we know what happens when the flux linking the coil decreases. An EMF is induced. Right? Let's say the voltmeter can measure this EMF. So what happens during this time is that there would be an EMF. So the voltmeter will measure a voltage. Okay. So suppose that I imagine plotting a graph of the voltage. And so I would have a certain voltage at the beginning as the flux starts falling, and because the flux decreases uniformly, this rate of change is the same over this time interval. It changes at the same rates during this time. So that means that during this time, the voltage induced, or the EMF induced, is constant. Okay, it's constant over this time until here. So this is how we would understand. This is how we would understand the connection between the flux and the voltage in this coil. Suppose that I think of some numbers for this. Suppose that the area is 1 meter squared and flux density is 1 Tesla in the beginning. Then, as we have seen just now, this means a flux of 1 Weber. So that would be 1 in units of Weber. That's how we might imagine it. Okay, so the starting flux is 1. Now suppose that I allow the flux to decrease to 0 in exactly 1 second. Okay, so I've set this up and I start turning down the magnetic flux density either by pulling a magnet away, or if I'm using an electromagnet, I would just turn down the current of the electromagnet. And I would adjust things in such a way that the flux falls right down to 0 after exactly 1 second. If I do that, the voltage induced, we can actually find the voltage induced because it's the rate of change of the flux. It just means that in this example, I can just take the change in flux in 1 second, which is just 1 Weber, and I can divide it by the time taken, which is 1 second. Okay, let's do a simple calculation. This is what I could do. I could say that the voltage induced is the change in flux divided by the time taken. Okay, and the change in flux in this case is 1 Weber, and the time taken is 1 second. So the answer is just 1. You can either call it Weber per second, which sounds really unfamiliar, or since we know it's a voltage or EMF, the answer is in volts. And this is the formula from Faraday's law. So this means that we know from Faraday's law that if this happens, if a 1 Weber of flux falls uniformly to 0 in 1 second, then an EMF of exactly 1 volt would be induced. So that means that if I plot this graph, I would see 1 volt. I will see a straight line at 1 volt. Okay, because the rate stays the same until the 1 second is up. So after 1 second, flux stops changing. So that means that the rate of change becomes 0. So therefore, the voltage will drop to 0 after that. Now, it is this description, this understanding that is used for the official definition of a Weber. Okay, let me try and write this out. So 1 Weber, 1 Weber is the flux linkage that if allowed to fall uniformly to 0 in 1 second, okay, induces would produce an EMF of 1 volt in a coil. And that is how the Weber is actually defined officially.